Okay. So, hello everyone. This is our third meeting. Today we'll discuss on those topics: basis, and especially basis, dimension, and coordinates.
Hi, can I ask a question?
Hello.
Hi, this is Nipendra. Can I ask a question?
Yes, please ask.
Yeah, so the question may be not related to this particular topic per se, but because I'm learning linear algebra to basically kind of get into some of the AI/ML stuff, right?
Okay.
I think there's a prerequisite for that, right? That's what I can kind of get there, right? So just want to connect the dots there, right? How does this will eventually connect there? So if you can just spend a few minutes, if you have some idea about that, that would be really helpful.
Okay, I will try to give those ideas. Wait.
I mean, only if it's possible. I don't want to kind of take
Yes.
away your time. Yeah.
Yes. Okay. Okay, so let us start. So, what is basis?
Okay. So if you're going that, so just as one question on that basis thing only.
Okay.
I was going through one of the video. In that, it was mentioned that for the R2 space, 1, 0 and 1, 1 is the basis.
Is
Right?
yes.
And now the idea is that if we remove one of the element, then it should not basically get the entire vector space there.
Yes.
So if we kind of, let's say, remove 1 1, then it just becomes only x, right? And that is not
Yes.
a
It
complete
will be exact.
that is not a complete thing, right?
Hmm.
Now on a similar thing, what is the and if you kind of remove 1 0, then it's x is equal to y. That is there, right?
Yes.
But
So,
how do we kind of cover the y-axis, right? Because the 1 0 part, right? So how is that being? So basically, how does if we take 1 0 and 1 1 as the basis, right? How does it covers the y-axis? Because we need to kind of take care of the entire R2 space, right?
yes. So basis means a generating set. What is generating set? First of all, so generating set means some elements. Suppose standard notation is E1 up to En. So this should generate whole space. This is not the whole space. Their
Okay.
union may not be whole space. For example, consider the minimal case. For example, so here x, you can see x-axis and y-axis. So x-axis and y-axis, that is this 1 0 and 0 1. This is not the whole space. Okay, or any multiple of 1 0, that is x comma 0, and any multiple of 0 1, which is 0 comma y. This may not be. This is not not the whole space. But what can we do? We can take their linear combination. Okay, so we can take x time 1 0 and y times 0 1. Now you can see this can be written as x comma y. That is any point you choose, I can give the coefficient x and y such that span of this set 1 0 and 0 1, this will give that particular point.
Okay.
For example,
Understood.
yes, you want to, so you are saying how can we generate this 0 comma 1?
Right.
Okay, so take 1 comma 1 and subtract it 1 0.
Mm.
Okay, now this gives 0 comma 1.
Understood. Understood. Now I think I got the point.
Yes.
Yeah, so that generation has not kind of in that. Okay.
Yes, yes.
Understood now. Thank you.
Okay, thanks. So first let us define basis. What is basis? Basis is, you can say basis is a generating set. Generating set, and another condition is it must be linearly independent. Independent. So a set S is said to be a basis if it generates the whole vector space and it should be linearly independent. Okay. In notation, we can write V is linear span of S, where S is linearly independent. What will be an example for this? So, as usual, R3. R3 is this three-dimensional space. It is x-axis, y-axis, it is z. So, the you can take this as a basis E1, which is 1 0 0, E2, which is 0 1 0, E3 equal to 0 0 1. Because any point, suppose xyz, be an arbitrary point chosen from this R3, you can uh, make it span, that is, it can be written as x e1 plus y e2 plus z e3. So any point belongs to the span of this e1 e2 e3. And moreover, we can see that those e1 e2 e3 is linearly independent. That is, you cannot uh, you cannot put this z axis in xy plane. This is the meaning of linearly independence. So why it is different from x? Because multiple of y cannot lie in x, okay, except the point 0. So mathematically, how do we verify? Take any linear combination c1 e1 plus c2 e2 plus c3 e3 and make it 0. Let this equal to 0. So this will imply c1 e1. C1 e1 means c1 100 plus c2 010 c3 001. And 0 means here notation it is 0 vector. This will imply c1 comma c2 comma c3 equal to 0, which is same as saying c1 equal to 0, c2 equal to 0 and c3 equal to 0 simultaneously. So therefore we conclude this is linearly independent set. This is linearly independent. Okay, Li. Consider an example. First of all, let us see some equivalent criteria for basis. So, basis is defined by linearly independent set which generates. That is, generating set or generator together with linearly independent. This condition, And this is equivalent to saying it is maximal linearly independent set. Independent set. And
Sir, question was, what is generating set? Not very clear.
generating sets means a set which span the vector space. That is, take any element V. So take any element V from the vector space, and suppose basis is given by this vector, uh, notation alpha 1 up to alpha n, and V is the given vector space, then V can be written as sum of those vectors. Okay. So linear span of B, this is defined as C1 alpha 1 plus dot dot Cn alpha n, where all Ci are from scalar field. Any F is the field, scalar field. Generating set uh, means this set. Okay.
Mhm. Okay.
Generating set, or equivalently we call it spanning set. These are all equivalent notations, and which is equivalent to saying uh, maximal linearly independent, dual of this statement, that is minimal generating set, smallest generating set. We are not taking every generator. For example, for this R3, for for this R3, you can take every vector, not only x, y, z, that is not only e1, e2, e3. You can take more vectors. For example, this is, you can include, for example, you can include 1, 1, 0. But the thing is, those will be not linearly independent. We need to take minimal spanning set. Okay. And only linearly independent set will not generate the whole space. We need to take maximal linearly independent set. For example, E1, E2 are linearly independent, but this generates only this plane, not the whole R3. So we need to take maximal linearly independent set. Minimal spanning set. And this is equivalent to saying that every vector can be written uniquely in terms of basis. In terms of that basis set, that is S. Suppose S, we are saying S to be a basis. Condition for S to be a basis. Those are the equivalent conditions. So for your particular problem, you can take any of the definition and you can work with that definition, because those are equivalent. You can take any definition for that particular problem, which definition will be helpful. You can take that definition. So question: find a basis for symmetric matrices. So V, here the vector space V V is space of all symmetric matrices. That is, V belongs to V is a matrix. V contains all matrices, square matrices, such that A transpose is same as A. Now you need to find the basis for this vector space. So, take any element. A will look like this. A11 up to A1n. Let us A11, A12 up to A1n. Similarly, A21, A22 up to A2n, and AN1, AN2 up to ANN. But here the space is only space contain only symmetric matrices. Therefore, A21 this is same as A12. Okay. And similarly, AN1 you can write it as A1n, and AN2 is same as A2n. It is symmetric. So if you reflect along diagonal, it will be symmetric. So A1 to this element will be same as A this element. 2 1 element will be same as 1 2 element. That's why I am writing same. Let A belongs to V. Then you can write A as you can write it as A11 E11. What is E11? E11 is the elementary, not E11. Instead of writing it as E11, you can write it as 1 0 0 0 everywhere. Okay. Now, if you take A12 out, then what will be inside? It will be like 0 1, and here is also 1, and everything else will be 0. Do this process until you finish. Last term will be ANN, and it will be 0 0 0 everywhere 0 except this place. So this is a spanning set. So what will be a spanning set? You can take, let S B is same as those matrices 1 0 up to 0, 0 0 up to 0, 0 0 up to 0, and similarly all the others matrices 1 1. Here it will be 1 1, and everything else will be 0. Similarly 0 0.
Question here.
Yes.
So what you're saying is that, like you told earlier, we have to take the maximum number of vectors, like the minimum. I think you said that, which will constitute a basis, right?
Yes.
So
Maximal
is this
linearly independent set.
okay? Maximum linearly independent. So these sets which are of 1 1, they are the maximum independent, linearly independent ones.
Yes, those are maximal linearly independent set. You're right. But we need to prove this, that it is maximal linearly independent set. We need to prove this.
Okay. So above this, the sum which we have written, like A11 plus A12 plus like that. So can we, like, what is that? That's not even a determinant, right? That's not a determinant.
This is a matrix. Yes, this is.
Okay. So So we have expanded this matrix in the sum form of
Some form of some other matrices.
linearly
Are,
independent
yes,
matrices.
yes.
Okay, okay.
Oh,
Okay, fine. Yeah.
and note that you cannot take this element, that is 0 0. This element is not allowed because this does not belongs to the vector space.
Sorry,
That
I didn't get what you're saying. Can you please tell?
E1 2. Do you
Hmm.
know this notation? Eij,
Yeah, yeah.
elimination matrices. It means 0 everywhere except this ijth place. Okay, 0 everywhere except ijth place. Ijth
Okay.
entry is 1. I am
Sir,
saying that
do we have two ones in the A12? There are two one, right? In the top. Yeah.
I am saying that this 0 1 0 0 0,
Yeah.
you
That is,
cannot take this matrix in
oh,
the spanning set. Why? Because this is not a symmetric matrix. Symmetry. It is not a symmetric matrix, so this does not belongs to the vector space. So you cannot take the span of Eij's.
okay.
You
So,
need to modify this. So that's why an arbitrary element, if you choose any arbitrary element, you can write it as linear combination of those matrices. What are those matrices? Those matrices are can be notationally it is same as Eij. Okay, when I
sir, if you don't mind, and actually it's not very clear
yes
that the second matrix which we have,
yes
it
you
has
can
symmetry.
see this, see that this matrix is symmetric matrix.
Yeah, because we want to maintain symmetric. We
Yes,
want to
you want
show.
to maintain symmetry.
Okay, so but then this will evaluate to. It will multiply A1 to both the places. Okay,
Yes, it will be A12 and it will be A12 again. So this
so
is the
we
thing.
will. Okay, okay. So we will not have this sum two times for two places. Only once is enough. Okay.
Yes,
Mm-hmm.
once is enough here. So you will take those matrices Eij plus Eji when I not equal to j, and you also take those matrices Eii when it is in diagonal line, then you just take Eii. For example, here you will take this one entry at
Yeah.
this diagonal and everything 0. So
Mm.
that's why explicitly we can write the spanning set as this. Okay. So S, if we write S to be this, then clearly, therefore, S span the vector space. Now, only spanning is not, uh, it is not enough to conclude that this is the basis. This is the basis for this symmetric matrices. So we need to check. We need to check S is linearly independent. So how do we check that? Let us try. So consider this C1. It is consider this linear combination Cij, Cii, Eii, and for these matrices Eij plus Eji, will take this Cij. Okay, consider this equal to 0, where uh, I runs from 1 to n, and here I comma j, I is strictly greater than j. So if you consider this to be 0, this will imply, if you expand, this is same as C11, C22 and CNN at the diagonal, and C, for example, if you choose I to be 1, then it will be C1 and something. For example, J to be 2. Here, let us take I is less than J, then it will be C12 and C12 E1. So what is C12 E12 plus E21? This is same as saying at 1/2th position and at 2/1 position both will be C12. And similarly, everything will continue up to C1n, and here also Cn1. N1 will be not present, C1n, because I is strictly less than j. This is 0. And this is 0 means everything is 0. Every Cii equal to 0 and every Cij equal to 0. Now you can conclude that S is also linearly independent. So first we have shown S is a spanning set. That is, any matrix, you have taken any matrix, you can write the matrix A as linear combination of those particular matrices. Okay, which is explicitly written as Eij plus Eji, that is flipping along the diagonal 1/2th entry plus 2/1 entry. Those are written in this. And another thing is Ei, diagonal entries corresponding to diagonal entries. That is 1, 0, 0, x everywhere. And similarly 0, 1 and 0, 0 everywhere. Those are written in the notation EII. Okay.
So can you please explain the purple equation once?
Which question?
The purple one, the last.
Yes. This step.
Yes.
Okay. So let us expand for one case. Consider C21, and instead of making it big, let us consider only 2 by 2 matrix. Then what will be E12? This is same as saying C11, 12, E12 plus E21. What will be E12? E12 means it is same as C12 into at 1/2th position it will be 1, and except everywhere it will be 0. Except this, everything is 0. Similarly, C12 times 2/1 position it will be C1, and everywhere it will be 0. Now, then what is the sum of this? This is same as C12 0, 0, 0, 0, 0 plus C12 at this place. Okay, so we can write C12 here. Now, is it clear?
Yeah, yeah. But this third line saying CII is equal to 0 and CIJ is equal to 0.
Yes.
How?
CII means all those for all I equal to 1 up to n, and here for all I greater than 0, I less than 0. Because what is 0 matrix? 0 matrix means this matrix, 0 everywhere.
Yeah.
And 0 everywhere means each term will be 0. Each term here, what are the terms? C11 up to Cnn.
Okay.
That's why
Yeah. I got
this.
it.
Okay, great. So therefore a basis for symmetric matrices can be written as S equal to all Eij plus Eji. Those are not enough. I is strictly less than j, or whatever you take. I is strictly greater than j will also work because this is symmetric. Union Eii, those diagonal E11, E22, those terms, I equal to 1 up to n. So this is a basis because this implies linearly independence, and first one imply it span the whole vector space. So if it is clear, let us consider another problem. So here it is given x minus x, y comma z. Those are the vectors. V equal to 2 by 2 matrices. This is the vector space, and W1 is a subspace of V, and W2 is defined by A, B minus A, C. All matrices of these forms, that is X, Y, Z, are from real number. Similarly, A, B, C are real numbers. Is it clear that W1 and W2 are vector spaces? Are W1 and W2 subspaces of the vector space? Are those spaces subspaces? What will be the answer? The answer is yes. Why? Because it is closed under addition and closed under scalar multiplication. Take any two element. Let us check for W1. So let x1 minus x1, y1, z1, and x2 minus x2, y2, z2. This belongs to W1. This imply if we take their sum, what will be the sum? So let V equal to this and V1 equal to this and V2 equal to this vector. Then V1 plus V2, or you can take the combination like this also, CV1 plus V2, where C is from any real, C is any real number. And this is same as Cx1 plus x2 minus Cx1 minus x2 and Cy1 by 2 minus Cz1 minus z. For this matrix, you can write it as Cx1 plus x2, and note that this term, sorry, this is wrong. Second term can be written as negative of the first term. So 1/2th entry is the negative of the 1/1th entry, first entry. Therefore, this also belongs to the space W1. Hence, W1 is closed under addition and closed under scalar multiplication. Okay. Therefore, W1 is closed under addition. Swati, your mic is on. And scalar multiplication. Hence, W1 is a subspace. we can define dimension of a vector space. What does this mean? So it comes from geometry. If you see R2, you can span the whole R2 by this x-axis and y-axis. That is, uh, in mathematical term, you can write R2 as linear span of those a basis, that is E1, E2. E1 means 1, 0, and E2 means 0, 1. Now, what will be for R3? R3 can be spanned by those three elements, E1, E2 up to E3. Now, those are three tuples, that is E1 are 1, 0, 0, and similarly E2, E3. So, a question arises that what will be the minimal number of elements which span the whole space? For R3, this is the minimal number of elements. That is, you cannot reduce those three elements to any other elements, 2 or 1. Then you will not get the whole R3. You will get a plane or you will get a straight line. Those will be the subspaces. But you cannot reduce this number. For R2, it is also same. R2 is spanned by those two elements or spanned by any other elements also. If you rotate XY axis, this is also a spanning set, and this is also a basis because those elements are linearly independent. Or you can take this line and these lines. Those two lines also span the whole R2. Okay. So dimension is defined by this. Dimension of a vector space V is the number of elements in a basis. Now question arises that if we can take different bases also. As earlier it was asked, R3 can be written as span of those E1, E2, E3, and it is also a span of these elements, E1 plus E2, E2 plus E3 plus E3 plus E1. Can you see that this is also a basis? If we give a name S, can you see that S is of basis? Let us try to see. First, take any element x, y, z. This from R3. This belongs to R3. X, y, z, it can be written as x times E1 plus y times E2 plus z times E3. And this is same as you can write in terms of those S elements. You need to write in terms of S elements from the set S. So how do you write this? X E1 plus y E2 let us write in this way. We don't know how can we write this, but let it possible we can write it in terms of those elements from S. So give it names. Let it is F1, it is F2, and it is F3. Let XYZ is some combination of F1, F2, F3. That is C1 times F1 plus C2 times F2 plus C3 times F3. Then it is same as F1 means U1 plus E2. That 1 and 1. First and second position will be 1. Everything is 0. Similarly, C2 is instead of writing this, let us C2 is E2 plus E3 0 1. F3 is 1 0 1. This is C1 plus C3, comma C1 plus C2, comma C2 plus C3. So this means simultaneously x equal to C1 plus C3, or we can rewrite it as C1 plus C3 equal to x. Similarly, C1 plus C2 equal to y, and C2 plus C3 equal to z. Can we solve this equation? Let us solve. Add those three equations. Then it will gives 2 times adding, will get 2 times C1 plus C2 plus C3. This is same as x plus y plus z. And this means C1 plus C2 plus C3. This is same as x plus y plus z by 2. So now you can solve, because 1, 2, 3, this is equation 4. Subtract 1 from 4. This will give C2 is same as x minus x plus y plus z by 2. And this is same as x minus y minus z by 2. Similarly, for C1 and for C3, from the symmetry, is it clear from the symmetry? No. Let us. So C1 will be subtract 2 from 4. It will give y minus this. So y minus x plus y plus z by 2. This is same as minus x plus y plus z minus z by 2. And similarly, C3 is z minus this, minus x minus y plus z by 2. Therefore, any element x, y, z can also be written as linear combination of f1, f2, f3, because solution exists. Solution is given by those three. So therefore, any element x, y, z, this can be written as this minus x plus y minus z by 2 times f1 plus this c2 x minus y plus minus z by 2 times f2 and minus x minus y plus z by 2 times f3. Therefore, f1, f2, f3 also generates the whole space. Span of this f1, f2, f3 is also R3. And another thing, you can check that those elements are linearly independent. Okay, because if this combination is 0, this is same as 0, then C2 is same as everything x, y, z, everything is 0. Then C2 is 0, C1 is 0, and C3 is also 0. Therefore, this is also linearly independent. F1, F2, F3 are linearly independent. Hence, F1, F2, F3 is a basis. Okay. F1, F2, F3 is a basis for R3. So from this, we can see that number of elements in the basis. Here it is e1, e2, e3, and here also in the second basis it is also f1, f2, f3. There are 3 elements for the vector space R3, and it will hold for any vector space. I want to say that number of elements in any basis for a given vector space is same. That is, dimension does not depend on the basis you choose. You can take any basis and you will obtain the dimension is same. That is, those bases will contain the same number of elements. You can choose f1, f2, f3 or e1, e2, e3. Those will be the same. There must be same number of elements in the basis. So from this you can say that you can see that any two vector cannot span the whole R3, because basis must contain 3 elements. Okay, because one basis for R3 is e1, e2, e3. So question, e1 plus e2 and e1 plus e3, is it a basis? The answer is no, because dimension of R3 equal to 3, because e1, e2, e3 is a basis for R3. Okay, so here is a question. Find a basis for W1. W1 and W2 are already given. Here the question was this. So question is, what will be the basis? What will be a basis for this W1? Find a basis for W1 and W2. As usual, first we'll try to write any element in terms of some particular elements. So pick any element from W1. It will look like, let.
Bittu sir, one question.
Yes.
Just to understand the question better, I mean, I am new to this, so that's why I'm asking. So we are saying that we have a matrix XX, YZ, where X, Y, Z belong to R, and
Yes.
we want to prove that W1, W1 is, we want to find the basis for W1, right?
Yes, it is also done. Yes, we need to find a basis for W1 and W2.
So when we are writing a matrix like the two-dimensional matrix with two elements in it, like X, X, and then Y, Z.
Yes.
So it is belonging to an R2 space, correct?
R4. There are 4 elements.
Okay.
That is, it belongs to M2 cross 2. But there are some relation. That is, you cannot choose anything for the second entry.
I got it. There is some relation. But isn't one row equal to one vector, like one in the space, one row? So there are two rows, and then each vector has two elements in it, like x and y, x and minus x. Then second is y and z.
Z.
So isn't it belonging to space R2?
Space R2 means which space you want to say?
Like to plane. I mean,
Oh, this is a 2 by 2 matrix, so
yeah,
it cannot belongs to a plane. But if you take this row space, that is, if you choose x comma minus x, this element,
yeah.
and y comma z, that is
Mhm.
span of these rows, then this will belongs to this will belongs to those R2. This
Okay,
contain in R2.
okay. But so now we are not taking it like this. Then how are we reading this matrix? Like, how are we looking at this matrix?
Uh, we know that any matrix M cross N, this is a vector space,
Yes.
which
But which
is, you can
dimension?
thought this as R to the power Mn. That is, there will be Mn independent entries. But here, instead of 4 independent entries, the second entries will depend on the first entry.
First entry. Okay. Yeah, relation I got. That part I got. That it cannot
Yes,
be just any entry. It will be related to the other one.
other one. Yes.
But dimension, I was just thinking, since we have an example here, like W1,
Hmm.
it is x comma x1, x comma minus x, and then we have y comma z. So, just I mean, I want to clarify with you, like, is it this particular W1 belong to vector space, or and then obviously based on relation we can find the sample uh, also.
Yes, yes. For example, if you see this R2, this is R2 plane, and a subspace, you can consider a subspace given by some relation.
Yeah,
So this R2 has dimension 2
yeah.
because R2 is generated by E1 and E2. So dimension of R2 will be 2. But suppose this is the line x equal to y, that is, it is generated by this x comma x, those entries.
Yeah.
Then what will be the dimension of this subspace W?
Okay. Mm-hmm.
Any element can be now written as x times 1 comma 1.
Mm-hmm.
Okay.
Yeah. Yeah.
Any element can be written as x into 1 comma 1. And a single element will always be linearly independent as it is
Mm-hmm.
not non-zero. So clearly it will be one dimensional because basis for this subspace will contain only one element. Therefore it is one dimensional. Is it clear?
Yeah, somewhat clear, sir. Yeah. I will probably like listen to you and then see.
Okay, okay. So let this be an element from W1. Element from W1. Then we can write this vector x minus x y comma z. This can be written as x times the similar tricks. If you take x out, then it will be x minus 1 minus 1 and it will be 0 0. If you take y common, then it will be, here it will be 1 and except everything it is 0. Similarly, take z common, it will be 0 0 0 and 1 1. Therefore now you can see that any element of this space can be written as linear combination of those three elements. So give it a name. Suppose this is alpha 1, this is alpha 2, and this is alpha 3. Then any vector V, it is span of those elements. So W1 is span of alpha 1, alpha 2, alpha 3. Because any element from W1 can be written as linear combination of those alpha 1, alpha 2, and alpha 3. And you can see that alpha 1 belongs to this W1, because here the form of this vector, it is 1 minus 1 0 0, that is second entry is negative of the first entry. Similarly, this also belongs to W1, because second and third entry you can choose anything, but the rules is that second entry must be negative of the first entry. Here it is true, and here it is also true. So all those three elements belongs to W1. Now the question is, are these elements alpha 1, alpha 2, alpha 3, are those elements linearly independent? So take the combination linearly independence. We need to show that. Take the combination C1 alpha 1 plus C2 alpha 2 plus C3 alpha 2 and set it 0. Let this be 0. Then what is C1? What is this sum? From this relation, you will get the sum is same as C1 minus C1, and here C2 C3. So this is 0 matrix. What is 0 matrix? Everything is 0. Therefore you get C1, C2, C3, everything are 0. Therefore alpha 1, instead of repeating, let us give names S. Therefore S is linearly independent. Now you can say S is a basis for W. Now the question, what will be the dimension for this space? You can see that basis contains three elements, alpha 1, alpha 2, alpha 3. Then dimension will be, which imply dimension will be 3. Swati, is it clear?
Yes, yes, sir.
Similarly, W2, this is the W2. You can write W2. It is easy, means similar to check that W2 is span of those set. Span of those elements. Here it will be 1, here it will be minus 1, 0 0, and 0 1 0 0, 0 0 0. So dimension of W2, it is also 3. Okay. Now there is another question which says, what will be dimension of W1 intersection W2? Dimension of W1 intersection W2. What will be the dimension of W1 intersection? So let us figure out what is the intersection. As we have already seen, W1 and W2 are defined by those relations. So W1 and W2 are defined by those relations. So any element, let A11, A12, A22, A, sorry, this is 21 and A22. This belongs to W1 intersection W2. So this belongs to W1 intersection W2. Therefore, this matrix A also belongs to W1 and A also belongs to W2. Now, what is the meaning of A belongs to W1? What relation do we need to satisfy? What relation? The relation will be the second entry, this second entry must be negative of the first entry. Okay. So A belongs to W1. This means A12. This is same as minus A1. And what is the meaning of A belongs to W2? Here the relation is third entry. It is negative of the first entry. Therefore A21 this will be negative of A1. So A21 is same as A1, negative of A1. Hence, therefore, W1 intersection W2, this can be written as matrices of this form. A11, and this is negative of A11, this is also negative of A11, and the fourth entry, it can be anything. Where A11 and A22 are coming from real number. Is it clear? Okay.
Yeah.
So now the question is, what will be the dimension of W1 intersection W2? So as usual, we will find a basis for this space and we will conclude what will be the dimension. So any element will look like this x, minus x, and y. This belongs to W1 intersection W2. Therefore, this x, y, we can write it as x times 1 minus 1, 1, and here it is 0, plus y times 0 everywhere except the last position. We can write this as a linear combination of those two matrices. This is beta 1 and this is beta 2. And you can see that this element, this belongs to W1 intersection W2 because it satisfies the criteria which says the second and third entry will be negative of the first entry. So second entry is minus 1, third entry is it will be minus 1. So this belongs to W1 intersection W2. Similarly, beta 2 also belongs to the intersection. Why? Because second and third entry is negative of the first entry. So therefore we can conclude W1 intersection W2 are spanned by those two elements, beta 1 comma beta 2. Now we need to check or we need to show those elements are linearly independent. So as usual, let C1 beta 1 plus C2 beta 2. This is 0. Where Ci from the scalar field R. Then this will imply C1 minus C1 because those combination are we know the what will be the combination. We can write it as this. This is 0 matrix. 0 0 0 0. Therefore, this will imply C1 is 0, C2 is also 0. Other relations minus C1 equal to 0, minus C1 equal to 0, those are redundant. Those are already coming from C1 equal to 0. So we have not written those relations. Hence this implies beta 1, beta 2. This is linearly independent. Li, linearly independent. Therefore, what will be the dimension of W1 intersection W2? Beta 1, beta 2 is a basis for the intersection. Hence, dimension of the intersection is 2. Okay. So that is how we find the dimension of a given space. We'll find a basis for that space. Now the number of elements in the basis will be the dimension. You can guess that dimension will be 2 because this matrix will it is just same as two tuples x comma y which are linearly independent, and everything except those are dependent on those entries. So you can guess we can pick two entries free. So there will be two free entries, and this concludes our guess. Okay. There is a theorem which says dimension of W1 plus W2. It is same as dimension of individuals but it may not be true. For example, R2, this subspace W1 and this subspace, this y-axis, this subspace W2, both are of dimension 1 because it is W1 is generated by E1, W2 is generated by E2. And we also note that the whole thing is generated by E1, E2. So we may expect the dimension of the whole thing, it will be dimension of the individual. Okay, but this is not true. Why? Take this example. Suppose we have given two space. W1 is the xy plane, which is generated by E1, E2, spanned by E1, E2, and W2 it is xz plane, that is spanned by E1, E3. Now the whole space R3 it is spanned by only three elements, E1, E2, E3. So it is not spanned by four elements, because you can see that one element E1 it is present in present in W1 space, and it is also present in W2 space. This extra term which presents in the intersection, it is creating a problem. That's why we need to subtract the intersection. Okay. So for our question here, for this question W1, W2 is already given. Here, what will be the dimension of their sum? W1 plus W2. What will be dimension of this space? So using this theorem, using star, we'll get dimension of W1 sum W2. This is same as dimension of W1. It was 3, I think. Yes, it was 3. Dimension of W2, it was also 3. And now intersection has dimension 2. Therefore, this is same as 4. Okay. Is it clear? Okay. If it is clear, just move to another problem. Okay. question. Given 4 vector, alpha 1 is 1 1 2 4, alpha 2 is 1 minus 1 minus 4 comma 0, alpha 3 2 minus 1 minus 5 comma 2, and alpha 4 is same as 2 1 1 6. Are those vectors linearly independent? What will be the answer? So let us check if it is independent or not. Okay. Solution. So one way is to check is using definition, that is let C1 alpha 1 plus C2 alpha 2 plus C3 alpha 3 plus C4 alpha 4, this combination is 0. Then we need to show all coefficients are 0. Okay. Coefficients are from the real number. We need to prove that all coefficients are 0. We cannot write 0 as a non-trivial combination of alpha 1, alpha 2, alpha 3, alpha 4. We need to prove that. So if we assume this to be 0, here 0 means it is tuple, that is 0 0 0 0. That is 0 means this 0. Now if we sum those elements using this combination, we'll get C1 plus 2C2 plus C3 plus 2C4, because C1 times this 2C2 2C C1 times alpha 1, this will give C1 here. C2 times alpha 2, this will give C2. C3 times alpha 3, this will give 2C3, because there was C3, so 2C3. That's why this will be C2 2C3 plus C4 2C4. Similarly, second entry will be C1 minus C2 minus C3 plus C4, and the third entry will be 2C1 minus 5C2 minus 4C2 minus 5C3 plus C4, and the last entry will be 4C1. 0 times C2 is 0, so we'll avoid. It will be 2C3 plus 6C4. The whole thing is 0 0 0 0, which is same as saying those individual entries are 0. That is C1 plus C2 plus 2C3 plus 2C4 is 0. And similarly, other elements. This and this is 0. This is also 0. And this is also 0. So everything is 0. Now you need to solve for C1, C2, C3, C4. If this imply all C1 up to C4 are 0, then we are done. That is, those elements are linearly independent. If there exists a non-trivial solution, then this will imply those elements are not linearly independent. Okay. So you can see we can write it as matrix 1 1 2 2 1 minus 1 minus 1 1, 2 minus 4 minus 5 1, and 4 0 2 6. You can see that those entries are 1 1 2 4, it is the column, and 2 minus 1 minus 5 2, it is third, and this second row, now second, it is second column. Similarly, fourth is now fourth column. That is why instead of uh, assuming this combination, we can directly take those entries to be column, or even we can take it in a row. That one, you can put 1 1 2 4 in a row, and this element in another. So 4 element you can put in a row. As we know, row rank is same as column rank. Okay, that is why we have taken this matrix. Now we need to solve. Okay, so for solving, we'll perform those row operations. So what will be the row operation? It will be 1 1 2 2. Now subtract.
R2.
Yes. R3 minus 2 R1, which is same as 0, minus 4, minus 6, minus 5, minus 9, 1, minus 4. Similarly, 4026 R4 minus 4 R1. It will give 0, minus 4, minus 6, and 4 times 2 is 8, so it will be minus 2. Now again we'll perform the row operations, but instead of doing anything, you can see that second row is second and third and fourth rows are linear combination of second rows. R3 minus 3 R1 and R4 minus 2 R2, those are R2. If you subtract the R2 rows, it will give 1 1 2 2, 0 minus 2 minus 3 minus 1, and now 0 0 0 0. Now you can see that it cannot have it cannot have only trivial solution, because rank of the matrix, rank of, so this is for row echelon form, we need to again reduce, but let us consider. So rank of the matrix A is same as rank of the reduced matrix, which is 2, because there are 2 non-zero rows. Okay, we can perform another operations to obtain 0 here and 1 here for row echelon form, but we don't need now, because we can see there are 2 independent rows. We cannot uh, reduce further. That is, we cannot make it 0, second or first row. So rank of the matrix A will be number of non-zero rows, which is 2, or number of pivots. Okay. Hence, what can you conclude now? That this system has a non-trivial solution.
Yeah.
Okay. For example, let us check if some solution exists. So if we reduce further, sorry, it will be 1 1 2 2 and 0 half 3 by 2, sorry, 0 1 3 by 2, that is multiply by minus half, r2 times minus half, and those are 0 0. Now again you can subtract. This will gives 1 0 minus plus half and 3 by 2. Similarly 0 1 0 0, and those are 0 rows. Therefore the system Ax equal to 0, this is our row echelon form. This and this system are equivalent. Rx equal to 0. Okay. So here x is this C1, C2, C3, C4. Now what is the meaning of Rx equal to 0? Then this is same as C1 plus C2 by 2 plus 3C3 by 2. This is same as 0. And the second row, it was not 0 0. It is 3 by 2 and half. And the second row will give C2 plus 3C2 by 2 plus C3 plus C4 by 2. This is 0. Rx equal to 0 gives those two equations, because other are 0 equal to 0. We have not written those two extra equations corresponding to third and fourth rows. Now you can see there are some non-trivial equations, non-trivial solutions. What will be the non-trivial solutions? Here an example will be like, so let us write the whole solutions first.
So even equation 1, we will have C3 and C4.
Oh, sorry.
Yeah, no problem.
Yes, thank you. It is C3 and C4, because C3 times half, C4 times 3 by 2. Okay, great. Okay. So all the solutions can be written by solution to star is given by span of those elements. So we can choose here the free, those are free columns, because pivots are only first and second columns. Pivots are in first and second columns. So third and fourth entry you can choose anything. You can choose 1 0 and 0 1 to be in third and fourth entry. So if you choose 1 0, what will be the solution? Put it in the equation. What will be the solution? C3 is 0, C3 is 1, C4 is 0. So what will be C1? C1, so if we put C3 equal to 1, C4 equal to 0 in first equation, this will give C1 plus 1 equal to 0. This is same as C1 equal to minus 1. And similarly, in second equation, if we put those things, we'll get C2 plus 3 by 2 times 1 equal to 0. So C2 equal to minus 3 by 2. So we can write it C2 to be minus 3 by 2 and C1 to be minus 1. In similar manner, if you put 0 1, 0 and 1, this will give C1 equal to minus 3 by 2. And again, if you put 0 1 here, then it is 0 and it is 1. So C2 is minus half. So you get, those are the solutions. Not those, but span of those two elements. This gives all the solutions. Okay. Can you recall how can we get the solutions. If you can recall, the solution, general solution to start, it can be given by this form. We have chosen those C3 and C4 are independent, so we can put C3 to x and C4 to be y. Then solving this will give C1 equal to minus x minus 3 by 2 y. Similarly, solving this equation, it will give C2 equal to minus 3 by 2 times x and minus half times y. And instead of writing this, we can write it to its span of those two elements. The nice thing is that we can write whole space in terms of only two elements. Only two elements define the whole space, because any element from the space from the solution space or null space, it can be written in terms of those two elements. Okay, you can see that x times this plus y times this will give this element, the general solution. Here x comma y are coming from R. Is it clear? Here,
Last part is not clear. Uh, this okay, even the yellow part, the last yellow line. How did you arrive at 0110?
yes, I have already said that second, third and fourth entry, those are free. Third and fourth column are free. Therefore, we can choose third and fourth we can choose those two entries, third and fourth, any independent points, any independent vector. So as we know, 1 0 and 0 1 is a basis for R2. That is why we have chosen 1 0 and 0 1.
Okay. Mm-hmm.
And this will give the solution, whole solution, using those. And instead of doing this, you can also do this. Because now also you can see that the space, null space, W, or null space, solution space, or whatever, null space, this, any element, if you copy this, any element can be written as x times minus 1 minus 3 by 2 1 0 plus y times minus, it was minus 3 by 2, sorry, y times minus 3 by 2 minus half, and here 0 and 2, 0 and 1. Okay, that's how we can give the spanning elements, the elements which span the null space. Is it clear?
Sir, 0110 is a basis for which space? Sorry,
This is for R2, 0 1 0 and 0 1. This is a basis for R2. That's why we have chosen 1 0 and 0 1 here, because those two entries are free. You can pick any two elements such that they are linearly independent.
Okay. So these are the linearly independent
Yes.
from R2. Okay.
So now you can see that those four elements are not, sorry, those elements are not linearly independent, because you have already arises the conclusion. You have already arises in the conclusion from this, because rank of R is since rank of the matrix A, it is 2, therefore there exists non-trivial solution which we have already determined. Hence C1, C2, C3, C4 may not be 0. Hence we can say the given set, if we rename it S, then S is not linearly independent. Explicitly we can solve those equations, and we can find the, for example, if you choose C1 to be -1, C2 to be -3/2, C3 to be 1, and C4 is 0, this will satisfy this equation. This will also satisfy this equation. So there exists some non-trivial solution. This does not imply C1, C2, C3, C4, every Ci are 0. This does not imply this. Because of the fact rank is not full. Rank is not 4. It is less than 4. So there exists non-trivial solution. Okay.
Sir, geometrically, what would this mean?
Geometrically means that though there are four elements, this does not span the whole R4. You cannot see R4, but it says that those 4 elements only span 2-dimensional plane. There are only 2 linearly independent elements.
So does that mean that
yes.
when we were reducing the matrices, we kind of found that out of these 4 vectors, only 2 are independent.
Yes,
Rest
2 are independent, alpha 3 and alpha 6, because those correspond to the pivot.
Okay.
Okay, only those 2 are independent. So you can write alpha 1, alpha 2 in terms of linear combination of alpha 3 and alpha 4.
Okay.
Now coordinate. In Cartesian system or polar coordinate, we know what coordinates means. Coordinates is a description which describes position of a vector. Okay. For example, if you consider R2, take any element 1, 2. This belongs to R2. So R2, this element 1, 2, this vector can be written as 1 times 1, 0 plus 2 times 0, 1. Therefore, if we choose B equal to the standard basis E1, E2, then we can see that 1, 2 can be written as 1 times E1 plus 2 times E2. Hence, coordinate of V with respect to this basis, this will be same as 1, 2. Okay. We have written it in column vector because you can say 1, 2 times E1, E2. 1, 2 times this is same as this. Therefore, we have written it in column vector. Coordinate is always written in a column vector. This is a format. So now you can ask what will be the coordinate with respect to some other system. For example, if you rotate the plane in some angle, for example, we can rotate about angle theta. Then what will be coordinate of the previous point. Suppose V is AB, any general point. Then what will be coordinate of this AB with respect to the new plane? That is, I am saying that was old system. We have rotated through an angle theta. And the point here is x comma y, or a comma b. The vector is given by a comma b. What will be the coordinate of this AB with respect to new system? Do we know the answer? It is very familiar that for rotation, the transformation is like those a comma b, this element with respect to new coordinate. Now new coordinate, this is these two axes will correspond to new basis, because this e1, it after rotation this e1 becomes cos theta plus cos theta comma sin theta. Sorry. E1 is now cos theta comma sin theta. And similarly, E2, it will becomes minus sin theta comma cos theta. So coordinate of a comma b with respect to the old system. V with respect to the old system, the standard basis E1, E2. This is same as the matrix AB, because AB, you can write AB as A times 1 0 plus B times 0 1. That's why we are getting this AB. The first coefficient is A and the second coefficient is B. Now, with respect to this new coordinate, this purple, what will be with respect to those new bases? That is E1, instead of E1, E2, now the basis is B dash, the new basis, which is same as first element cos theta comma sin theta. E1, E2 was 1 0 0 1, but now it is more complicated. It is cos theta sin theta and minus sin theta cos theta. Now, what will be the coordinate of this point with respect to the new system? What will be the coordinate? This AP, it will change. So how can we determine? This is the question. Okay. So let us try. So we can solve for, let C comma D, or let X, Y be the coordinate with respect to B dash. Okay. Then we'll have this X, Y, that is the AB, that point can be written as X time this element cos theta comma sin theta plus Y time the second element minus sin theta comma cos theta. This will imply this is same as x cos theta plus minus y sin theta comma x sin theta plus y cos theta. So we'll have two equations. First equation is x cos theta minus y sin theta. this is same as A, and the second equation x sin theta plus y cos theta, this is same as B. And you can write in matrix form cos theta minus sin theta cos theta times xy equal to A. Hence, xy is inverse of this matrix. Cos theta minus sin theta cos theta, inverse of this matrix times AP. What will be the inverse? Inverse will be cos theta, and here it will be sin theta minus sin theta times A. So it is same as A cos theta plus B sin theta, and minus A sin theta plus B cos theta. Therefore, now you can conclude that x and y are, x is this and y is this. Hence, coordinate of xy with respect to the new basis. This is a new basis. That is cos theta comma sin theta, this vector and this vector. This constitutes new basis. And with respect to new basis, the coordinate is now different, because xy is now not AB. xy is not AB, but it has some extra terms. Okay. So with respect to two different bases, we'll get different coordinate. The coordinate will depend on how you look. Okay, from where you are looking at those vectors. From which system? It will depend on the deformation of the system. For example, here is an easy example. So this point 2, 2, 2, if you, here are the unit vectors, it is 1, 0 and 0, 1 is the unit vector. Now if you stretch the, that is, if you assume this to be your unit vector, that is, this was e1, e2 basis, instead of this 1, 0, you are assuming 2, 0 to be the basis, 2, 0 and 2, 2, 0, 2. This is your basis. With respect to those two bases, those two elements, you can write it as 2, 2 as 2, 0 plus 0, 2. That is f1 plus f2. Hence, 2, 2 with respect to coordinate of 2, 2 with respect to the our as usual basis, it was same as 2, 2. But with respect to the new basis, it is 1, 1 with respect to the new basis b dash. Because now the system is different. Okay. Here is a question. Given alpha 1 is 1, 0, minus 1, alpha 2 is 1, 1, 1, and alpha 3 is same as 1, 0, 0. Given b equal to alpha 1, alpha 2, alpha 3. This is an ordered basis. Ordered basis means you cannot change the order of the elements. Okay. you cannot interchange the order. So what will be the coordinate of a given point? Suppose 1, 2, 3, or suppose 1, 1, 1. Question 1. What will be the coordinate of 1, 1, 1? Any guess? 1, 1, 1. So it can be
This
written as,
0, 1, 0.
yes, 0 times alpha 1, 1 times alpha 2, plus 0 times alpha 3. So coordinate of 1, 1, 1 with respect to the basis B, this is same as 0, 1, 0. Okay. And in a similar manner, so here you can see the difference. With respect to the standard basis, the coordinate will be 1, 1, 1, because E1, E2, E3 are the standard basis. But with respect to this system, this basis, the coordinate is different. Okay. Now we give a general question. What will be the coordinate of any arbitrary point ABC with respect to this system? What will be the coordinate? So we can write let x, y, z be the coordinate. Instead of x, y, z, we can take x1, x2, x3 for linear equation be the coordinate of ABC. Then clearly ABC is a comma b comma c. You can write it as linear combination of those bases, x1 times alpha 1 plus x2 times alpha 2 plus x3 times alpha 3. And this will gives what is x1 times alpha 1? x1 times 1, 0 minus 1. This is same as x1, 0 minus x1. Similarly, x2 times alpha 2. This is x2, x2, x2. And what is x3 times alpha 3? It is x3, 0, 0. This is same as ABC. So you can say x1 plus x2 plus x3 equal to a. Let us write properly. x1, x2, x3, comma x2, comma minus x1 plus x2 equal to ABC. This will give a system of linear equations. x1 plus x2 plus x3 equal to a, x2 equal to b, x3, sorry, minus x1 plus x2 equal to c. So to solve the system, we can use the usual trick 1, 1, 1. The system can be written as how to solve. And this is ax equal to b. We can write the augmented matrix. This is same as a times x equal to b, where b is same as minus abc. So we can rewrite the augmented matrix AB, which is A 0 1 0 minus 1 1 0 B C. Now reduce it. So what is the process of reduction? One 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 0 1 0 AB and R3 plus R1, which will give 0 here, and it will be 2. And now the third term is 1. It becomes C plus A. Now again, you can apply R1 minus R2 and R3 minus 2R1, 2R2. Subtracting this, you will get 1 0 1. Here it is A minus B, and it remains fixed. It will be 0. Here 2 will get cancelled, and it is 1. C plus A minus 2. R3 minus, sorry, R1 minus R3. This will give 1 0 0, and here A minus B minus this minus C plus. So let us do this in a rough work. A minus B minus C plus A minus 2B. This is same as plus 2B minus B, which is B, and minus C. So it is B minus C. 0 1 0 B 0 0 1 C plus A minus 2B. So this is the solution. Okay, this Ax equal to B. Now this becomes, actually we have performed A inverse. We have multiplied A inverse in both sides. So this equation star becomes A inverse times this Ax equal to A inverse B. That is x equal to A inverse B, and this is that x. Okay, therefore the solution is x1 x2 x3 is same as B minus C B C plus A minus 2. Okay, so this is the process. First, you will write in terms of alpha 1, alpha 2, alpha 3, the given basis. And now, this will give some equations, put it into a matrix form, and as usual, we'll solve for x. So, what will be x? Just perform row operations until you get identity in the left. And here, the given the new thing, it will give the solution x, because we have here we have performed A inverse, and the right hand side we have also performed A inverse. This is actual A inverse B. A inverse B is actually this. That's why we are getting the solution. Okay. And also note another thing, this equation, this 1 0 minus 1, this is same as the first given element, and similarly the second and third row obtained from the second and third vector. Okay, so you can solve the equations. You can directly solve from this step. Just put the first, second and third basis element into this form, and you will solve for ABC. consider another question. Given consider the polynomial space P2. P2 be the space of all polynomials of the form a plus bx plus cx square. Right? A, B, C are from real number. Okay. This will form a vector space under the usual scalar multiplication and addition by term by term addition. Now the question is, and given a basis, ordered basis B, which is same as given by G1, G2, G3, given ordered basis, where G1 is given in this form 1, G2 is x plus 1, and G3 is x plus 1 whole square. The question is, what will be the coordinate of a general point C0 plus C1x plus C2x square, this vector, with respect to the basis B, the given basis B. What will be the coordinate? So here the trick is, you can write G1 as, we'll first write it in terms of standard basis. So G1 can be written as 1 times the 1 time 1 plus, you know that 1x x square is a basis for polynomial, because any element from the polynomial can be written in this form. So you'll write in terms of standard basis. The given basis can be written as 1 times this plus 0 times x square. Similarly, G2 can be written as 1 times x, 1 times 1 plus 0 times x square, and G3 is can be written as, it is actually expand this x square plus 2x plus 1, so 1 plus 2 times x plus x square, 1 times x square. So now you note that, therefore let suppose B1, B2, B3, this is not there, be the coordinate with respect to the new system, new basis B, or with respect to the given basis B. Then in the previous example, as you have seen in the previous example, you may write those coefficient in column. So it will be 1 0 0, 1 1 0, and 1 2 1 in the column, and this will be our C0, C1, C2 x square, because V also can be written as C0 times 1, C1 times x plus C2 times x square. So here you can write it as C0, C1, C2. Now solve for the following. Okay. Now use the row reduction, you will get something. And if you assume it to be A and this is B, then A inverse B will give you the vector B1, B2, B3. Okay, this is how you can find coordinate with respect to any system. We'll always try to write in terms of a system we know, and now we just solve for the new system. Okay, that is, it can be given by A inverse B, where A is the transpose of the coefficient 1 0 0 1 1 0, this is written here, and 1 2 1, this is written in third column. Now solving this will give you the required B0 B1 B2 or B1 B2. Is it clear? Okay. So if you have any question, please ask. Or otherwise, you may leave. Okay, thank you everyone.
Thank you, sir.
Thank you.
Ritu sir, one question. Actually, if I have some doubts, apart from the
Oh,
question.
sorry. I'll reply to all those queries. Okay.
No, that's okay. I mean, suddenly
Those
say
portal.
that is the only. Can you share your direct email so that we can write to you?
Yes, you may write, but I'll reply in this portal also. So
Okay, fine.
now
Okay.
I have not seen earlier. Sorry for.
No. Yeah, thank you.
Okay.